Welcome to our glider project. So the requirements for this project are that the glider had to be 50% balsa wood by weight, the aspect ratio had to be at least 5, the maximum wing loading of the glider was 0.5 grams per centimeter squared, it had to fit into a 16 by 16 inch box, it couldn't have any sharp edges to prevent injury, it had to be hand thrown, which includes no automatic or remote control of the glider, and it must remain intact for the duration of the flight. It also must fly at least 20 feet on level ground. The first step in the design process was requirement analysis. We had to make sure that every iteration of our glider fit all the requirements listed previously. Then we had to optimize our glider designs for distance. Alternatives for design were dihedral versus no dihedral, where dihedral provides improved stability during flight and no dihedral does not provide this benefit. A forward placement of the wings provides improved stability and a mitigation of the negative influence of turbulence during flight. And square versus tapered wings. Squared wings provide generally more lift because there's more area, and tapered wings provide improved aerodynamics. The size of primary components, so the wing sizing, we wanted larger wings for improved lift, and we wanted a larger chord length for improved weight, which makes it easier to throw. Design decisions, so again we decided on large square wings for improved lift, we decided on using a dihedral for improved stability, and we decided on forward wings, again for improved stability during flight. For balancing and testing, we used an iterative process for weight addition, where we would add a large amount of weight and then reduce weight each time until we find an optimal amount of weight. We would weigh it during each iteration to ensure that we knew the exact measurements, and then we would measure the flight distance and compare it to the 20 feet mark that we had to hit. For iterations, we had larger wings, support beams, better manufacturing, and weight properly balanced during our later iterations, which will be covered later.
So for our design drawing, we showed our initial design. For the front wings, we decided 18 by 4.5 centimeters each, and when we decided the dihedral design, we decided to do a tilt degree angle attack based on our research. And for the rear wings, we did 4 by 3 centimeters each. The fuselage length was 30 centimeters. Vertical tail was 3 by 4 centimeters, with the top part of the tail being smaller than the bottom. And we did 8 grams of balsa wood and 7 grams of Play-Doh. So for our glider balancing calculations, we calculated a coefficient of drag, coefficient of lift, and our center mass. For the coefficient of drag, based on thin airfoil theory, we got 0.04. For the coefficient of drag at 0, which is less polished invisible parts gliders based on research. And we calculated our coefficient of lift to be 0.2574. Our aspect ratio is 8, which is greater than the requirement of 5. And then E, which was 0.80 based on rectangular wings. We got coefficient of drag to be 0.0433. And our coefficient of lift we calculated using the coefficient of lift equation, with lift equaling mass times gravity, which is 0.147 newtons. Our density was 1.8 kilograms per meter cubed, which is the average in Atlanta. And our velocity that we calculated to be averagely thrown for each iteration we made was 0.7304 meters per second, and our surface area is 0.0162 meters squared, which gave us a coefficient of lift of 0.2574. So continue with our calculations. Our center of mass, you sum up the mass times the length, or where the position of that part on the glider is, and then divide by the total mass, which our total mass was 0.015 kilograms or 15 grams. And based on all the calculated masses for each part and where they were based on R, we got our total center of mass to be 0.063 and 0.0029 in the Y direction meters, or 6.3 centimeters in the X direction, 0.9 centimeters in the Y direction, which is 6.3 centimeters in the X direction leaves us just below 3/4 quarter length of the chord, meaning that it is a little bit below what is desirable, but is very close to it, that we could simply add a little bit more mass to make it to that length. And as you can see, our entire glider was able to fit in the 16 by 16 box, and based on iterative design process and reflection on our final design, we decided that we could have made our wingspan wider to be able to go diagonal across the 16 by 16 box to get a total wingspan of 22.6 if we wanted to redesign inches.
For design iterations, our first design had a poor wing gluing process, which was previously described. We glued the wings directly onto the 3D components. It had small wings, again because of this flaw, the wings were broken off when they were glued. And an improperly balanced mass because we didn't do enough iterative mass testing. And this design led us to about 45 feet of distance, and that was outdoors by the AMS. And then our second design had a proper wing size because there was no issue in the gluing process. We had the parchment paper so the wings could be attached correctly with no damage to them. And it had a properly balanced mass because we had more iterations of mass testing. And it flew about 55 feet, but only achieved 35 feet on flight day. So this is their first design iteration. On the left you can see with the configuration of mass, and as you can tell it has very short wings, again because of the failed gluing process that caused part of them to be damaged.
So as you can see with our final design, we decided to do a dihedral for our glider along with supports on the bottom so that the wings were more flexible and less likely to break. Overall, we had the Play-Doh at the front to move the center of mass forward and the horizontal tail wings to provide more stability to our glider in the rear, along with the vertical tail to help with the flight path of the glider.
This is a video of our final test flight. It's a little hard to see in the video there, but it went about 35 feet. So for further additions to a next iteration of our glider, we would include a negative angle of attack on the horizontal stabilizer, which would improve stability and fix the pitch-up problem that we currently have. We would include taper wings to improve aerodynamics of our glider. We would have longer wings because after talking to other groups, we realized that we could fit 22.6-inch wings on the diagonal span of a 16 by 16-inch cube. We would add a 3D printed component to add a throwing hold to make it easier to send a further distance. And we would ensure that the center of mass is 1/4 chord length on the glider because ours was slightly off.
And here are all the citations and resources that we used throughout the process to help in our design. Thank you for listening today.